Cycling is an activity enjoyed by families and athletes alike. But when accidents occur, there is limited data available to investigators to help them determine causes for certain situations. That's why ARCA Incorporated, experts in forensic engineering, teamed up with us computer engineers in Penn State's College of Engineering to develop our capstone project, the measurement of perception reaction time, also known as PRT, of cyclists. Our task was to create a testing apparatus and environment to record a cyclist's reaction time along with his or her hand position and exertion. The setups would be utilized by ARCA to build a database of reaction times for cyclists under different conditions and environments. We began by using the requirements given to us by ARCA to brainstorm our approach to tackle the problem. The requirements stated that there needed to be two setups, a laboratory and a road setup. Parameters, such as hand position, were to be entered at the beginning of a trial. Randomized visual stimuli should be presented to the cyclists throughout their trial, and their reaction time, movement time, heart rate, and exertion should be recorded during this response. Lastly, the apparatus should be bike transferable, it should be able to calculate the average and standard deviation of the recorded data, and it should feel natural to the cyclists. Our idea to meet these requirements was to have a core Arduino and sensor system that could be used in both the laboratory and road setups. The only change in these two setups would be how the visual stimulus was delivered to the cyclist. In the laboratory, the bike would be mounted to a stationary trainer, and the stimulus would be presented via a random LED lighting up on an array of LEDs around the perimeter of a television, displaying a first-person biking video to distract the cyclist. For the road test, the cyclist would be riding around in a normal environment. However, they would have a helmet with a fixed LED array on the visor, which would illuminate a random LED at a random time for them to press the brake to. We would utilize pressure sensors on the handlebars and a reed switch on the brake lever to sense when the cyclist's hands moved or pulled the brake to record the reaction times. We would also have a wireless bike crank mounted power sensor and a arm-worn heart rate sensor on the cyclist. The combination of data from these two sensors should depict the cyclist's exertion at time of reaction. Finally, to make our system user-friendly, we would have a micro SD card and a computer-based program with a GUI that would allow the user to set the Arduino settings before a trial and transfer the recorded data back onto the computer after the trials. Once we started building, we ran into some problems such as our pressure sensors melting when we tried to solder to them, which we solved by getting these clamps to solder to, which then clamped onto the sensors. Our next problem was that our Bluetooth power meter was not compatible with our bike, but we solved that by having ARCA send us out a compatible crank for our bike and then putting the bike in a shop to have them attach everything correctly. Then we moved into the testing phase where we tested our Arduino code and sensors on a prototyping breadboard. Then we individually tested and calibrated each pressure sensor on a spoon handle to replicate a handlebar. And finally, after a lot of testing and building, we had our finished product. We were able to maintain a clean design by utilizing a wire sleeve that ran the wires along the bike frame to the handlebars. Once there, we ran all the wires underneath sports pre-wrap to keep them away from the rider's hands when moving positions and pulling the brake. The LEDs on the visor of the helmet are perfectly positioned for the rider's peripheral vision and are not too bright due to the built-in eye protection of the helmet. This is our finished circuit with one Arduino Nano, one Arduino Nano BLE, an SD card reader, and a Bluetooth module. It is powered by a 26,800 mAh portable battery which is stored in this pouch along with the circuit in a protective case. The last step of our project was to design the GUI or graphical user interface of the program that would allow the user to set the settings for the trials and to read the data after the trials. This GUI is shown here and also demonstrates how the calculations and data are displayed after the trials are finished. In the end, we met all of our sponsors' requirements and remained under budget, which is a success in our eyes.